Good morning, everyone. Can you hear me well?
Yeah, we can.
You can? Okay, great. My name is Norma Elias, and I will be your instructor for this course. Everybody is in mute. Everybody, I would like you to unmute. I mean, to mute yourself, and feel free to unmute whenever you want to ask a question or answer this question. I also have chat, so you guys, if you have anything on the side you want to tell me, you can put it on chat. It's in front of me. I can read it very well. Okay, so I first go through the syllabus very briefly. The syllabus is in your is on Brightspace already, so you guys can look at it at the meantime. So my name is Norma Elias, and my office is in the CLO building, 348. My phone number is useless. Do not call me because usually I do not answer my phone. My email address, you guys have it as well. And my office hours are, let me see what I gave you, 2 to 3 on Monday, Wednesday, 12 to 1 on Tuesday and Thursday, and by appointment usually. Now the book, this is the book. Did you guys have access to the book? Were you able, anybody had any difficulty getting the book? Okay, great. So the course content, I can read them. A lot of things will not make sense to you at this stage. So we're going to basically learn how to solve linear system, what a vector space is, what a linear transformation. So we're going to study that throughout the semester. So reading them now will not really make much sense to you. The logic of the course, the logistic of the course, we will have a homework. So every time we meet, like today, you will have a homework. But I do not collect the homework. So the homework is for you to do. And the way I handle the course usually is that at the beginning of every hour, every time we meet, the first thing I do in class is I ask you, do you have any questions from the homework? And it will be totally up to you to ask me questions from the homework. Meaning that if you don't do the homework, basically you will not pass the course. So doing the homework is absolutely crucial in this course. I do not collect it, so which give you time really to do it. And my quizzes will be totally based on this homework. The exams will be based on the homework. So not doing the homework, it's really, really, really gonna affect you. So every day I come to class, the first thing I do is questions. Do you have any questions from the homework? Quizzes. I give 7 quizzes throughout the semester. Usually, I would have given you a quiz 1 next week and a quiz 2 4 weeks later. But because of the special circumstances this semester, I'm giving you quiz 1 and quiz 2 at the same time, and they will be November 11. Hopefully, I will be there that day because the idea is that I'm going to be off only for 4 weeks. So I'm going to give you both quizzes to 11. And then the remaining, you have the date right there. I will try the best I can to stick to the timing of the quizzes. But only exception is going to be quiz 1 and quiz 2 will be the day I come back. So which is to 11, just because of the logistic of giving you a quizzes when I am not on campus. Now the exam, you have 2 exams and the final. The exam 1 is February 27, exam 2 is April 10. And this is the date for the final. And your grade distribution is 25% quizzes and attendance, 45 on the exam, and 30 on the final. So this is briefly the how the course would work. Grading scale is just the usual grading scale, nothing really specific about it. Attendance is absolutely crucial. I usually take attendance every day, every time we meet, I meant. When I am on Zoom take the attendance for me, so I don't really have to be concerned with it. Otherwise, when I come to class, I will pass a sheet, and this will be the way I will take the attendance. And bright space, you have everything. I mean, that's how I communicate with you. You will have, of course, the grade, your homework, the solution to your quizzes, the review for your exam. Everything will be there on Brightspace. Office hours, I strongly encourage you to come to my office hours. And if you can not make it, just talk to me and we can arrange a time to meet. And do not wait till you come to my office hours. So catching up in this course is very, very difficult. So once you get behind, you're really, really in trouble. So please do not shy away at all to stop by my office hours. Okay. One important thing about the course before I get started is the following. Linear algebra is at the same time an easy course and also a hard course. What's easy about it? What's easy about the course that the course does not requires a lot of techniques. So it's not like Calculus 2, where you have techniques of like just technique for integration. You have so many of them. Testing sequence divergence, you have a lot of that. Linear algebra is not like that. Most of the techniques in the course, we're going to learn them in the first 3 weeks. After that, we have the techniques. After that, it's going to be really a lot of vocabulary. So the course has a lot of vocabulary that you guys do not know. And if you miss on the vocabulary of the course, you literally will fail the course because that's what the course is about. So it's a new vocabulary, a new language that you have to learn. And that's the hard part of the course. So techniques is not hard. Vocabulary is hard. If you miss on it, that's it. That's what the course is about. So whenever I'm going to introduce a word that supposedly I say linear combination, I explain it, I give the definition. It's up to you to know what it means. Otherwise, the course builds on itself. If you miss the vocabulary at the beginning, you're going to miss the course. Besides this, the course is not hard, but as I said, you have to keep up with me continuously. Any questions before we get started? Okay, so please don't shy away. Don't be shy. Just ask your question. Use chat to answer questions. So it's up to you to make those 4 weeks as pleasant as possible. Right. So we get started. So what we're going to start by today, and the first actually 4 lectures, is how to solve a system. So before I give you the definition, if I tell you, give me a linear equation in one variable. So what do I mean a linear equation is one variable? So something like that, 3x equal to 4. That's a linear equation with one variable. And if I ask you to solve it, okay, that's solving it. X equal 4/3, we'll solve it. Now, what's a linear equation? So this is linear equation with one variable. What's a linear equation with two variables? 3x plus 4y equal to 6. So that's a linear equation with 2 variables. Okay, we can have a linear equation with 3 variables. So I will have 3x, 4y. I can just plug in another one. 3z equal to 4. That's a linear equation with 3 variables. So what does the word linear mean? Linear mean is that those unknown x, y, z come with a 1 power. It means there is no square. So that's what really linear mean. Linear mean also that those unknown x, y, z are not multiplied by each other. So the way they are is a constant times the first plus a constant times the second plus a constant times the third. Now we can have also linear equation with 5 unknowns. I mean, I can keep adding, and adding unknowns. Okay. So I can have a linear equation with 10 unknowns. So once we have a lot of unknowns, we run out of letters to write them. So the way we're going to write a linear equation in like 10 unknowns is something like that. Instead of writing x, we're going to write x sub 1. Instead of writing y, we can write x sub 2, and so on and so forth. That's how we're going to write a linear equation. Okay, so I start with the formal definition now. So section 1.1, system of linear equation. Definition. What is a linear equation? A linear equation in n unknown, x1, x2 through xn, is an equation. Now, equation means equality. That's what an equation means, equality between two things. It's an equation of the form a sub 1 x1 plus a sub 2 x2 plus etc. a sub n xn equal to b. An equation means you have inequality, where b and a1, a2, a2an are usually known. So the unknown are, okay, the unknown are x1, x2 through xn. a1, a2 through an are called coefficient, and usually they are given to you. Okay. Now, if I moved the paper and you guys didn't finish writing, please let me know and I bring it back. So please, very comfortable in communicating with me. Okay. So let us see example of linear equation. So example of linear equation. So let me give you a bunch of equations and you have to tell me whether they are linear or not. So that's really my question. Suppose I take the following. The question is linear or not, because we have to understand the word linear. Okay, is this linear? Yes or not? Quickly. You can put on chat your answer.
Yes.
Yes, absolutely. Now, xy plus z equal to 2. Linear or not?
No.
Absolutely not, because here the unknown are multiplied by each other. That's not linear. So x squared plus y equal to 4. Linear or not?
Not.
Absolutely not, because x is squared. So linearity is very, very specific type of equation. Not every equation you see is linear. This is the meaning of the linear equation. Now, in this course, we are more interested in a system of linear equations. So what is a system of linear equation? A system of linear equation is nothing more than a collection of one or more equations together. So let us define a system. A system of linear equations is a collection of one or more linear equations that involve the same unknown. So we just put basically 2 or 3 equations together, and we call this a system of linear equations. So something like that. So let's say x plus 2y equal 4. I'm just making things up. X plus y equal 1. That's really a system. Now, what is a solution of a system? So if I have an unknown, the solution will consist of n numbers. So the solution of a system is a list of numbers that satisfy each equation. So since we have a bunch of equations, a solution is something that should satisfy every equation. Finally, a m by n system is a system of m equations and n unknown. So whenever we're talking about m by n system, the first one tells you the number of equations. And this always refers to the number of unknowns. Okay, so m by n system, the first letter, the number of equation, the second is the number of unknown. Okay, so for example, as I said, if I move the paper ahead of time, let me know. So let's see example of that. Let me consider the following equation, this following system. x1 minus 2x2 equal to 4, x1 plus x2 equal to 1. So this is, we call it two equation. That's a 2 by 2 system. Two equations to unknown. Now, who can give me a solution of this system? Just by eyeballing it if you want. Who can give me two numbers that satisfies both equations? One and two. One and, no, two and minus one. Okay, is your classmate correct? Let's check. If I put 2 here, minus equal 4, check. Now if I put 2 here, 2 minus 1 equal 1, check, absolutely correct. Okay, another example of a system. Okay, for x1 plus 2x2 plus x3 equal to 2. That's the first equation. Equation 2 is x1 plus x2 plus x3 equal to 2. Now, so far, most of the time, you guys have seen system. Of course, you've seen system. The number of equations and the number of unknown are the same. In this course, we don't put this restriction anymore. We can have more equations than unknown, and we can have more unknown than equations. So we're not restricting ourselves to this situation. So this system here is 2 by 3 system. Remember, the first one tell me the number of equation. The second tell me the number of unknown. So we have 3 unknown. Okay, who can eyeball a solution? So the solution here have to consist of 1, 2, 3 numbers. Who can think of a solution? Anyone? Okay, Isaiah give me 0, 0, 2. Let's see, is your classmate correct? 0, 0, 2, of course, 0, 0, 2, both are satisfied the solution. Can anybody think of another one? Okay, so the question is, this is going to have a lot of solution. So one of the things we're going to learn is how to find all the solution of the system. So it's not easy. I mean, all of you, you're looking at it, you found wonderful, you find one of them, but this is going to have infinitely many of them. So there are a lot of values who's going to satisfy both equation. So the question is, what are they and how can we find them? And that will be the goal of the first 3 lectures of the course. All right. Now we're going to talk a little bit about the simplest of system, this one, system, the 2 by 2 equations, because it's actually going to tell us a lot of things. So I'm going to talk a little bit about solution of 2 equations with 2 unknown. Now the variable, sometimes I'll write xy, or xyz if I don't have a lot of variable. And sometimes you write x1, x2, x3. So I want you to be comfortable with both notation. First, let me consider the system, x minus 2y equal 4 and x plus y equal to 1. So that's a system of two equations, two unknown. And you guys gave me the solution of that. You gave me 2 minus 1 is a solution. That's a solution. But now, geometrically, what does the solution represent? Can anybody tell me what does it represent geometrically? A point on the xy, absolutely, absolutely. So every solution, let me cancel this. Every solution of this equation, we can think of it like this. Suppose this is the xy plane. And every solution of this equation is a point on the line given by x minus 2y equal 4. So let us draw this line. If I put y0, x is 4, that's a point on the line. And if I put x equal to 0, y is equal to, if y is 0, x is equal to 4, my apology. And if x is 0, y is equal to minus a half. So that's this line here. That's the line x minus 2y equal to 4. Every solution is a point on this line. Now, this one, x plus y equal to 1. That's also a line. And x plus y equal to 1, it means if y is 0, x is 1. And if x is 0, y is 1. So that's the solution right here. So the solution is the intersection of both lines. So geometrically, that's a solution. All right. Based on this geometry, and it's unique, so we have only this solution. Very simple question. Give me example of a system, two equation, two unknown, that has no solution. So now we understand this geometrically. Can you give me a system, two equations, two unknown, that has no solution? Parallel line, absolutely parallel line. So let me say I put this one, x minus 2y equal to 4. Who can give me the second one? So there will be no solution. So I'm going to draw that here. Give me the second one, so to avoid a solution. Anybody can think of another equation? Oh, I like that. X minus 2y equal to 8. So x minus 2y equal to 8 is going to be something like that. So absolutely no solutions because those two lines are parallel to each other. They have the same slope, absolutely. So no solutions. Okay, and actually, if you look at it, there is no way you can find two numbers that satisfy x minus 2y is 4 and x minus 2y equal 8. Those cannot really work with each other. Okay, so the system has no solution, period. Now, my last question, again, all of them are simple questions. Who can give me a system with infinitely many solutions? Again, 2 by 2.
Two lines with the same slope.
The line, same slope. We need actually more than that because this will make them parallel. Okay, your classmates say identical line. Absolutely correct. Basically, you have to give me the same line. That's the only way I can have infinitely many solutions. They have to be the same line. So who can give me the second line? Who can play a game and give me another equation? Not exactly the same, but almost the same. Right. Your classmate multiplied across by 8 and tell me, okay, this one. This line and this line are absolutely the same because you just multiplied across by 8. So we're not really changing the line, we're just playing a game. But this one will have infinitely many solutions. So this is a very, very simple system of two equations with two unknown. And let's see what the scenario have. System of two equations of two unknown is possible to have one solution and infinitely many, or it's possible to have no solution. So we're going to define the word consistent now. A system will be called consistent if it has at least one solution. And I will give you a definition in a minute. So those two systems, there is one solution, infinitely many, those will be called consistent. So a system that has at least one solution will be called a consistent system. System with no solution will be called inconsistent. Okay, so a simple example to show you the larger picture, which is this is the situation for every system. And this would lead us to the following definition. Okay, here we are. Definition. A system is called consistent if it has at least one solution. It can have infinitely many, but at least there is one, we call it consistent. A system with no solution is called inconsistent. Okay, so that's the first vocabulary word we learned today. So consistent versus inconsistent. Okay. Now, another rule concerning linear system that will be important for us. Rule. If I go back to a 2 by 2 system, can a 2 by 2 system have exactly two solutions? Yes or no? Can a 2 by 2 system have exactly two solutions? It can have unique solution, infinity. Can it have exactly two solutions? What do you think? No way. Absolutely no. Because you have two lines. Either they cross one point, or they are on the top of each other, or they are parallel. So there is no way I can have two solutions. Interestingly, that this holds for every system. So what do I mean by that? Any system of linear equation, the word linear is crucial, has either a unique solution, one, infinitely many, or no solution. So every system, so we will work with a lot of linear system, but we know ahead of time that when we solve it, we're going to have either one solution or a lot of them, infinitely many, not a lot, infinitely many, or no solution. So that's hold for every system of linear equation. So what do I mean by that one more time? Okay. It means that a consistent linear system cannot have exactly two solutions or finitely many. So we cannot have two solutions. It's either infinite or unique. So now I have the following question for you. Who can give me example of a 2 by 2 system with two solutions? Be careful, I did not write it. Who can give me example of a 2 by 2 system with exactly two solutions? Be careful, the word linear has been dropped from the question because this is not true for linear system. I'm here. Think of a system where, think graphically. Two intersecting circle, but I don't know how to write the equation. Okay, that's fair enough. All right, so I'll draw the picture that your classmate has in mind, and then I will write the equation. So let us say I have this circle, and let us say the radius is 1. Okay, so what's the equation of a circle of radius 1? X squared plus y squared equal to 1. All right, that's equation of definitely that's an equation. Now, what's the other equation? I can have two circles, but who can give me something easier than a circle? So already it's not linear because I don't have then I take the following, x equal to y. The line x equal to y. Definitely the system is not linear because the first equation is not linear. So this is a circle and this is a line. Of course, we have exactly two solutions, not only one. So linearity is crucial to guarantee the existence of, if the system is consistent, of one or infinite, nothing in between. All right. Now we are going to basically start solving system very easily. But before that, I need a definition. Okay, equivalent system. Suppose you have two m by n system. Remember, m equation and unknown of linear equation. What does it mean to say they are equivalent? Two m by n system of equation are said to be equivalent if they have the same solution. So we have two systems. So for example, let's make this clear. So you don't have to write this because we're going to do it. Suppose I take the following system, x plus y equal to 4, and then x minus y equal to 6. And then I do the following. I take the system, x plus y equal to 4, and I multiply the second one across by 2. So I'm not really changing it. Those systems are equivalent. Everything, every number that will every two number that will satisfy this system will satisfy that because the only thing I did is I multiplied across by 12. So that's what we mean by equivalent system. Now, solving a linear system. So we're gonna solve our first solution for a system, and this approach we will use is called the Gauss elimination method. And the goal of it is to start with a system and replace it by another one which is equivalent to it, but easier to solve. So we're going to solve a system. That's the first system you will solve today. And the way we're going to do it, that's the approach that called Gauss elimination, is we're going to take the system, substitute it with something easier to solve. Okay, so let us solve the following system. All right, so this is my system. X minus y minus z equal 2, 3x minus y plus 2z equals 16, and 2x minus y plus z equal 9. And the question is, solve the system. It means find the numbers x, y, z that satisfy all the three equations. All right, let's see how we're going to solve it. All right, the approach is the following. What do we mean by elimination? So what we are going to do at the beginning is the following. And I'm sure a lot of you have seen this way of solving. It's called the elimination method. This is, we have x in the first equation. We're going to use this x to eliminate the x in the second equation. So how are we going to do that? We're going to do it as follows. We're going to take the first equation, multiply it across by minus 3, and add it to the second equation. Okay, so we're going to do the following. We're going to replace, I'll write the second equation, which I called equation 2, by the following. Minus 3 equation 1 plus equation 2. Okay, so what I'm going to do is the following. I'm going to take the equation 1, multiply it by 3, add it to equation 2. And whatever I get will be my new equation 2. So I will do the first one very, very slowly. minus 3 equation 1, it means minus 3x minus minus plus 3y minus minus plus 3z equal minus 6. I will add it to this one. Equals 16. So minus 3 equation, I add them. The goal is to eliminate this x from the second equation. Minus 3x plus 3x cancel each other out. Then I will have here 2y plus 5z equal to 10. And this would be my new equation 2. So from here to here, I will write what I did. I will not touch the first equation. That's remain. The second equation is going to be replaced by that. So this would give me 2y plus 5z equal to 10. The third equation will not be touched as well. So we will learn an algorithm to solve a system, and we all will use the same algorithm. That's the algorithm we are going to be learning. Now, an important point that those two systems, those are equivalent. It means that every xyz that solve this will solve that. The reason is the first equation is the same, the last one is the same. This is the only one, the second one is the only one that's changing. But if we think a little bit, every three numbers that satisfy the first equation will satisfy that. And every three numbers that satisfy the second equation definitely satisfy this. So those three numbers, if they satisfy this one and that one, they will have to satisfy their sum. So every three numbers that satisfy the three equation, the original one, will satisfy the new one. So we are not changing the solution, we are manipulating the equation. Now step 2 is the same. We're going to try to eliminate the x from the third equation. So the way we are going to do it is we use the first equation to eliminate the x in the second and third equation. So I think the pattern now is clear. How do you want me to eliminate this x? Quickly. So I will not touch the first one. I will not touch the second one. I want to try to eliminate the third. How do you think I will eliminate it? Quickly. Exactly. So I'm going to replace equation 3 by minus equation 1 plus, minus 2 equation 1 plus 2 equation 3. Okay, so I'm going to multiply this by minus 2 and add it. This time I will not do the long way, we'll just do it together. Minus 2x plus 2x, that's a 0. Minus minus, that's 2y minus y, that's a y. And that's minus minus, 2z plus z, that's 3z. And minus 4 plus 9 minus 4 plus 9 is equal to 5. So now I ended up with this system. Okay, so first step, we're eliminating all the x's except the first one. Now I'm going to repeat the process, but to this system. So now I'm going to, I will not touch the first equation anymore, and I'm going to start working with this subsystem if you want. So what do you think I want to do? Okay, multiply row 1 and add to third. Multiply row 1 by minus 2. All right, will this be correct though? If I multiply the first row by minus 2 and add to third row, no, this will not do it. I cannot touch the first one anymore. I cannot touch the first equation anymore because if I touch the first equation, I will create an x in the second or third equation, which will be problematic. Okay, so yeah, okay, so this doesn't work. Anybody has any other suggestion? Exactly. Anybody has any other suggestion? What do you want me to do? The idea now is to start eliminating the y from those equations. All right, so let me tell you what I'm going to do. Because I'm lazy, I don't like to compute a lot. I'm going to switch to two equations. So I'm going to take equation 2, so replace equation 2 by equation 3, and vice versa. So sometimes we call this equation 2, switch it with equation 3. Now, this will not affect the solution because we're switching equations. So I'm going to write this as y plus 3z equal 5 and 2y plus 5z equal 10. Okay, I have now the system. And I ask you the same question again. How do you want me to eliminate the y in the third equation?
Multiply the second equation by -2.
Right. So now we're going to do the following. We're going to take the second equation multiplied by -2 and add it to the third equation. And the result of this operation is basically going to be my new equation 3. All right, so let's do that. X. So I will not touch anymore the first equation. I'm not going to touch the second. Now here, minus 2y plus 2y, 0, I eliminated the y. Now right here, I will have minus 5z, sorry, minus 6z plus z, which is going to give me minus z, equal minus 10 plus 10 equal to 0. Okay, so what I did so far, starting from the first equation, we actually, the only thing we did is we're not trying to change the solution, we are manipulating them so we have a simpler system. Now I'm gonna reach here. Can you guys solve the system? Can anybody give me the solution of the system? I want you to look at it and tell me. 750, absolutely correct. So let us see what's happening right now. This system is very easy to solve because z is 0. There is no way out. Y plus 3z equal 5. If z is 0, y equal to 5. We have y. If z is 0 and y is 5, I can solve for x and I will get equal to 7. This is called back substitution. So again, a new word we introduce. So we're going to use what we call back substitution. So back substitution, it means we're going to start substituting from the bottom all the way to the top. So we know that z equal to 0. Now, y plus 3z equal 5. So I'm substituting backward, which will give me y equal to 5. And the first one, x minus y minus z equal to 2, will give me x. So this is a 5, x equal to 7. And the solution now is the following, 7, 5, and 0. Okay, that's what we are going to be calling the Gauss elimination method. So let me a little bit summarize it one more time, what we did. So we started with a system. You know, it looks fairly complicated, and we'll try to solve it. So the way we did is like this. We start with this x, and we use it to eliminate the x in the second and the third equation. And we use very simple operation that did not alter the solution of the system. Now, once we did that, we're done with the coefficient of x. We start working with the y. We want to eliminate the y from those equations. So I said, it's easy to flip them. You don't have to do it this way. It's easy to flip them. So I will have coefficient of y here is 1, just to make things easy. So I switched these equations, and I ended up with this system. Now I repeated the process. I wanted to eliminate y from the last equation. So I did eliminate y. Once I eliminated y, I was able to do back substitution very, very easily. So I isolated z, I found z, I backed up, I found y, backed up, found x. Okay, so that's really gonna be the idea that we will use to solve a system. But now what we are going to do is we're going to introduce the idea of a matrix, which is going to help us solve the system with less writing. So matrices. Please ask questions if you have any questions. Keep the way we solve the system in mind because I need to come back to it later. So now matrices. What is a matrix? A matrix is nothing more than a rectangular array of numbers that has the following form. So you took two brackets, and then you put a bunch of numbers inside the bracket. So any numbers you want, you can put them inside the bracket. So 1, 2, 3, 4, -1, 0, 2, 3, 1, 6, 7, 8. So a matrix is just a rectangular array of numbers that has the following form. This is called the first row of the matrix. So that's first row, second row, third row. So these are called the rows of the matrix. Those are called the column of the matrix. So that's first column, second column, third column, fourth column. And this matrix is called, this is a 3 by 4 matrix. That's a 3 by 4 matrix. The first term is the number of rows, always, and this one is the number of columns. Number of rows and number of columns. So a m by n matrix is a matrix. It means just an array of numbers put between brackets. M by n matrix is a matrix with m rows, and that's important. That's the number of rows, and that's the number of columns. Okay, rows, columns. So a 2 by 3 matrix, it means just this rectangular array of numbers. It means I have 2 rows and I have 3 columns. That's how we talk about a matrix. Now we are going to use matrices to represent a system. So every system, we're going to represent it by a matrix. Okay. So a matrix as a shorthand to write a system. So far we work with system, but now we're gonna write them in an easier way. So suppose we have the system, the same one I gave you a minute ago, but I put x1, x2 instead of x, y, z. Now to every system, we are going to associate two matrices. All right. One we will call the coefficient matrix. Coefficient matrix. So it's the coefficient matrix. It's a matrix that has inside it the coefficient of the unknown x1, x2, x3. So it goes like this. The first row of the matrix is coefficient of x1, coefficient of x2, coefficient of x3. The second row, coefficient of x1, coefficient of x2, coefficient of x3. The third row, coefficient of x1, x2, x3. So that's what we will call the coefficient matrix. So the column, the first column will have the coefficient of the first variable, 1, 3, 2. The second column has the coefficient of the second variable, x2, and this has the coefficient of the third variable, x3. So that's called the coefficient matrix. And we associate to a matrix, but another a system, another matrix called the augmented matrix. Augmented matrix. Now, what's the augmented matrix? It's basically the coefficient matrix, but we augmented the constant term. So it is like that. I'm going to put here a dotted line. The book does not use it, but I want you to use it, which separate the coefficient piece from the augmented piece. It goes like this. So the first row would be 1, minus 1, minus 1. We add the constant term at the end, which is a 2. So it's basically represent the whole equation in a way. Now the second one would be coefficient, coefficient, coefficient. That's the constant term. And the third one is 2 minus 1, 1, 9, the last term. So that's the augmented matrix. And we're going to start representing every system by the augmented matrix. So let's make sure that we understand this. I mean, it's fairly simple. So please, I repeat, if I am going fast or you cannot write, let me know. Help me out. Okay. So now suppose I ask you the following. Write the system that correspond to the following augmented matrix. So I give you the augmented matrix, and the question is to find the system. So question number 1, the system that corresponds to this matrix, how many equations does it have?
2 equations.
How many? 2 equations. And how many unknown would it have? Remember, that's the coefficient of x1. The second column, coefficient of x2, this will be the coefficient of x3. So the system that corresponds to it will be the following. It's a system which have 2 equations and 3 unknown, because this is the augmented term. So the system would be x1 plus 2, x2 plus 0, x3 equal to 4. The second equation would be minus x1 plus 2x2 plus 6x3 equal to minus 5. Okay, so starting basically today almost, a lot of time, instead of giving you the system, they will give you the augmented matrix. And it's just because it's easier to work with, as we will see very soon. So suppose I write the following system here. x1 minus x2 equal to 4. x1 plus 4x2 equal to 6. x1 minus x2 equal to 7. Okay, so that's the system I have. So it's a system of 3 equations and 2 unknown. So the augmented matrix is going to be what type of matrix? How many rows and how many columns? The augmented. So the augmented matrix is, how many rows will it have? Anybody wrote something? I don't know.
3.
3. How many columns is going to have? Coefficient? No, why 4? It's going to be also 3. We have one unknown, two unknowns. So these are the columns, and that's the augmented term. So it's going to be a 3 by 3 matrix. That's the augmented. All right, so let's write it down. Coefficient of x1 is 1 minus 1, 4. 1, 4, 6. And finally, 1 minus 1, 7. So the augmented is 3 by 3. The coefficient is 3, the number of equation, and 2, which is the number of coefficient, because the coefficient matrix does not have the augmented term in it. Okay, so every system we represented by matrix. Every matrix, augmented matrix, we can use it to represent a system. So when I'm giving you a system, I will be all the book. It will either give it to you this way or that way, whichever they feel like. All right? Okay. Now, okay, next time we have a lot of vocab to develop, but I have to motivate a lot of vocabulary. So what I'm going to do now is I will go back to the system we solved together. And I will solve it all over again, but using this time the matrix idea. So I will go back to the system. Let me find it, this one. And now the idea is use matrix notation to solve the system below. So this is the system I solved. X minus y minus z equal to 2. 3x minus y plus 2z equals 16. And finally, 2x minus y plus z equal to 9. So we're going to work with the same system, but this time I'm going to introduce the idea of a matrix to solve the system. So how does it work? So whenever we have a system, we're going to immediately write the augmented matrix that correspond to it. So the idea is that writing XYZ all the time is just too much work. We can simplify that. So this is the augmented matrix that correspond to it. 3 minus 1, 2, 16, 2 minus 1, 1, and 9. Okay, so that's the system. Now let us remember how we solved the system. What was the first step? This is the coefficient of x here. I wanted to eliminate the 3x. So I multiplied x by 3 and I subtracted. So that's what we did. So what we did is we took the first equation, we multiplied it by minus 3, added to the second equation, and this, if you want, became our new equation 2. So that's really how we start solving. And when we did that, we got x minus y minus z equal to 2. I did not touch the first. I did not touch the last one. The only one was altered was the second, and we eliminated x in here, and here we got 2y plus 5z equal to 10. Though that's what we did. So now I'm going to move to the matrices, and I'm going to do that matrix. Let us see what did we do here. When I multiplied the first, before I back up a little bit. In the augmented matrix, remember, this is the coefficient of x, coefficient of y, coefficient of z, the constant term. Coefficient, coefficient, coefficient. Now, when I saw what I did, I multiplied this by minus 3. It means I multiplied the coefficient here by minus 3, this coefficient by minus 3, this coefficient by minus 3, this one by minus 3, and I added those to the coefficient of x here, coefficient of y, coefficient of z, coefficient of 16. This is equivalent to do what on the matrix? Equivalent to do the following on the matrix. Take the first row, this term, multiplied by 3, by minus 3, and add it to this coefficient. Multiply this by minus 3 and add it to that. Multiply this by minus 3, add it to this. Multiply this by minus 3, add it to 16. So performing this operation on the equation is equivalent to do the following on the matrix. Again, replace row 2 by minus 3 row 1 plus row 2. Because I'm really working with coefficient. X, Y, Z, you can think of them as a placeholder. I'm really working with the coefficient. So let us see what I mean by that. It means I replace the second row by minus 3 row 1 plus row 2. Means the first row hasn't been touched. The last row hasn't been touched. It's the second row that I'm going to work with. Multiply this by minus 3 and add it. This is going to bring me the 0. That's the 0 I got in here. I multiply this by minus 3, which gives me a 3. 3 minus 1, it's a 2. So I'm doing the same thing, but instead of keep writing x, y, z. Now right here again, I multiply this by minus 3, which will give me a 3. 3 plus 2, which gives me a 5. Multiply this by minus 3, which gives me minus 6. And I add it to this, which will give me the 10. So instead of working here, I'm going to be working right there. That's how I'm going to simplify the solution process. Right, now let me keep going. I'm going to do exactly the same thing. What did we do after that? Once we eliminated the x here, we wanted to eliminate it from right there. So, which will be equivalent to do what on the augmented matrix? The first row we don't touch. We take the first row, multiply it by minus 2, and add it to the last row. The idea is to eliminate the x from the third equation. So instead of working here now, I'm going to work immediately right here. And what I'm going to do, I'm going to replace the third row by minus 2 row 1 plus row 3. So instead of doing that, here I'm doing it right there. So let me do this. And it will be a little bit easier, I think. So I did not touch the first one because it has the coefficient of x here. This is I did not touch it because I already eliminated my x in here. And finally this one, I want to get rid of this 2. So I took multiplied this by minus 2, added 0. Multiply by minus 2. 2 minus 1, I get a 1. Multiply this by minus 2, which gave me a 2, plus 1 gave me a 3. Multiply this by minus 2, minus 4 plus 9 gave me a 5. And that's exactly what we did when we performed this on the equation. So equation-wise, that's exactly what we did. And here I got y plus 3z equal to 5. Nice. What did I do after that? You guys remember? Remember what I did here to solve the system. I wanted to get rid of the y's. Anybody remember how did I do that? Switch row 2 and row 3. Exactly. I switched them just to make the math much easier. So now what I did is, from here to here, I switched row 2 and row 3. Switched row 2 and row 3. So I ended up with this. One, minus 1, minus 1, 2, 0, 2, sorry, 0, 1, 3, 5, and 0, 2, 5, 10. Okay. And finally, I said, okay, I eliminated coefficient of x in all the equation except 1. I have to keep the 1. Now I wanted to eliminate the coefficient of y. So I'm basically working with this little piece right there. So this is done with it. I don't work with it anymore. So what we did is that, okay, to eliminate the coefficient of y, we have to multiply the second row by -2, which is equivalent to multiply the second equation by -2 and add it to this one. So this was my last operation. So I will write it down. Okay. So from here to here, what we did is I took the second row, so I replace the third row by -2, row 2 plus row 3. So that's what we did. So the third row, we did that to it. The first one, we didn't touch. The second, we did not touch. That's what we did. -2 plus 2, it's a 0. -2, it's a -6 plus 5, it's a -1. And this gives me a 0. So we reach that stage. Once we reach that stage, we realize that I can get z immediately from the last equation. And we got y from before because I have z to be 0. And then I got the x from the first equation. And then we use back substitution. So how we are going to solve system starting today? What we are going to do is the following. We start with the system and we don't do that anymore. We will start with the system and we move immediately to the matrices. And we will do work. We're going to work with the matrix, and that's what will be the content of next lecture. So we're going to do those operations, like replace a row by something. We do all those operations until we reach a stage where we realize that, okay, now we can stop and we can solve. So what we are going to be talking about next time is the following, and in the time left for us. First, we are going to define those operations. We're going to give name to those operations that I did on the matrix here. Second, what we are going to do is when we solved a system, we knew exactly when to stop. We knew that we stop when I got minus z equal to 0 because I can back substitute. So we're going to describe, if you're working with matrices, where do you stop and you start solving. So we're going to describe the shape of this matrix. So today, what we are going to do is basically talk a little bit about those operations that I did on this matrix. And we are going to call them elementary row operation. So let me start it. All right. Elementary row operation. And all the definition I will do today and next time work for any matrix, not necessarily the augmented. Yes, I will. It's going to be, I'm recording it. I'm recording the lectures and I hope to be able to put it on Brightspace. Yes, I will. All right. Elementary row operation. And this applies, as I said, to any matrix, not necessarily the augmented. When we solve the system, what type of operation we did? The most important operation is this operation where we were able to get the 0. So I can eliminate the coefficient of x. And the way we did this is we multiplied a row by a constant and added to another one. So this operation is going to be called replacement. So what is a replacement? So replacement is the idea of replace one row, I call it Ri, by the sum of itself and a multiple of another row Rj. So symbolically, we write Ri plus Krj become, sorry, this is not understood, the new Ri. Okay, so what this row operation is the operation that I used a lot. That's what I'm talking about. So when I went from this to here, by multiplying by -3 the first row, adding it to the second, I did what we called replacement. So I'm going to write this as -3 R1, multiplied row R1 by -3, added to the third row. That's what we call replacement. And the result is becoming my new row 2. So I replaced row 2 by the sum of itself and a constant multiple of another. That's the first operation that we will use a lot. That's called replacement. The second operation we use is called interchange. It means interchanging two rows. So Ri will be, so we can put two brackets like this. Ri interchange with Rj. So this is the second row operation we do. Okay. A third operation that I did not use today, but we will do is called scaling. What is scaling? It's also easy. Scaling means multiply all entries in a row by a non-zero constant. So I take a row. Sometimes we realize that multiplying by a constant make our life easier. So this operation is called scaling. It means you take all the entries in a row, you multiply them by a non-zero constant. And we write KRI become the new RI. Means we substitute Ri by a constant multiple of itself. Those operations are called elementary row operation, and those are the operations that we will be working with basically to the end of the semester. So those are basic operations we perform on the matrix that's going to help us solve any system we want. So I repeat, the three operations, elementary operations are replacement. We replace a row by the sum of itself and the constant multiple of another. The other operation is interchange, we just interchange two rows. The last operation is scaling, which is multiplying a row by a non-zero constant. And why non-zero? We will answer this question in a minute. Okay, now more definitions a little bit. Row equivalent matrices. All right, what's a row equivalent matrices? Two matrices are said to be row equivalent if one matrix can be transformed into the other by a sequence of elementary row operation. And we write A equivalent to B. I read again and then I'll explain. So if you have two matrices, we call them row equivalent if one is obtained from the other by performing row operation. And we write A equivalent to B. It means that we get B from A by performing elementary row operation. It means the operation I've been talking about. So, for example, so let us see example. I give you time to write. So example is, suppose I take the following matrix. Sorry. Suppose I take the following matrix. 1, not necessarily augmented, just a matrix. 2, 3, 4. Okay, that's, I will call this matrix A. And -1, 1, 6, 2. Okay, and I'm going to perform the following operations on it. So the first operation is replacement. I'm going to take the first row, multiply it by 1, add it to the second row, and this will be my new row 2. So I'm going to substitute or replace the second row by minus row 1 plus row 2. So this will give me the following. 1 minus 1 is 0, a 3, a 9, and a 6. This is the, so that's the replacement. I'm going to do another replacement. I'm going to do the following. I'm going to take the second row and multiply it by a third. So that's, I'm going to do scaling. 1/3 row 2 will become my new row 2. That's the scaling. So what do I mean by that? I keep the first one the same. The second row I multiplied by a third. Multiplied by a third, multiplied by a third, multiply it by a third. Those are the row operation I am talking about. So that's the replacement and that's the scaling. Now suppose I call this matrix B. Okay, so we say that the matrix A is equivalent to the matrix B. So we will write a lot this equivalent. It means I got B from A by performing those elementary row operations. Okay, any questions? Now, the other thing is the following, a note, important note as well. Fact about row equivalence. Right. I read it and then I explain it. If the augmented matrices of two linear systems are row equivalent, so we have two linear systems. If their augmented matrices are row equivalent, then the two systems have the same solution sets. So what is it I am talking about? It means that, okay, suppose I have the following system. Actually, I can write here. So suppose I have the following system, x1 plus 2x2 plus 3x3 equal to 4. So that's my system. And minus x1 plus x2 plus 6x3 equal to 2. That's a system. Okay, so the augmented matrix of it, 1, 2, 3, 4, minus 1, 1, 6, 2. That's the augmented. And let me perform an operation on it. So I'm going to multiply, so minus R1, like the previous example, into R2. So 1, 2, 3, 4, 0, minus 2 plus 1, sorry. 2, sorry, plus R1, my apology. 1 minus 1, 0, that's a 3. 3 and 6, that's going to give me a 9, and that's give me a 6. And let us say I performed another operation here, the scaling operation. So I multiplied this by a third. So all those are equivalent matrices. 0, 1, 3, 2. So this matrix and this matrix are equivalent. Now, if I write the system, so I go back here and I write the system that corresponds to this matrix, which is x1 plus 2x2 plus 3x3 equal 4, and then x2 plus 3x3 equal to 2. The idea is that this system and that have the same solution. Okay, so when I perform those row operation on a system, I don't really changing the solution of the system. So if I go from here, I perform my row, I perform my row, those two are row equivalent. The system that correspond to them will have the same solution. And that's really give us the reason why we will be able to use row operation to solve a system. Okay, I stop here today. And next time, what we are going to be doing is actually learn the algorithm, a correct algorithm to perform those operations and start really solving system in a much easier way. Okay, any questions before I let you guys go? The homework. the way I put the homework, if you go to Brightspace on the content, there is a module called homework. You open this module, and every time we meet, I assign a homework for the following hour. So, for example, for tomorrow, your homework is already on Brightspace, and it's written homework for like 1/16/25. So this will be the homework that you have to do for next time. As I said, I do not collect them, but every time we start the hour by going through the homework. So please do them. That's the only way out. Okay, any questions before I let you go? Okay, have a great semester. Bye-bye, guys.